we've now got a session which is around technology, and we've got 9 companies who are looking to present their technologies to us. So I'm going to pass over immediately to Torleif Madsen, who's CEO of Compact Carbon Capture AS. Over to you.
Thank you. We are a compact carbon CO2 capturing solution, recently purchased or acquired by Baker Hughes. So I think this is the proof of what we are trying to achieve, or what we are achieving. This is a rendering of our plant in the middle. And if you look to conventional CO2 capturing technology represented by TCM Mongstad, the world's largest CO2 capture test center, on the right-hand side, you could see the difference. And actually, the TCM Mongstad plant has the capacity of capturing 100,000 tons CO2 per annum, while the 3C technology in the middle is able to capture more than 200,000 tons of CO2 on the same concentrated flue gas. So it's a double of capacity with a significant reduction in size. The leaning tower piece isn't catching any CO2, but it's there to represent or compare the size of a 60-meter tall tower. And as you can see on the far right, the stripping tower of the conventional technology, we have actually, if you could swap slides again, we have placed it inside a 40 feet standard ISO container. So this is the plant. The flue gas is entering on the left through a fan to equalize pressure drop. It's going in an upward direction through the absorber where the solvent is introduced in a cross-flow rotating direction and exited on the top without CO2. The loaded solvent is taken into the stripping unit where it's heated up and releases the CO2. So you can deliver the CO2 at an overpressure of about 4 bar, which will be energy saving in the liquefaction. If you could swap slides again. We are standardizing this in modules. So instead of tailor-making CO2 capture plants for each point of emission, we are standardizing in strategic sizes, and then we are scaling by modules. We could have as little as 10,000 tons per year, which would be suitable for very small emissions and preferably utilization cases for the CO2, up to medium points of emission in a roundabouts of 1 million tons per year, which would be huge waste energy plants or large industrial sites. If you swap slides again. So our key features is of course the size. With a 90% reduction on the core components, we find that we could reduce the size of the plant for up to 75%. And this allows us to use a lot less building materials to build these plants, and that would have a direct effect on the capex. So we're aiming for a 50% capex reduction, which will of course be case specific. By adding this module-based scalability to the equation, we find several benefits. One of them is that you do not have to invest in a full capacity of your production right away, but you could deploy one module and then build up a price premium for emission-free products, and you could then add on modules as the market is going in the right direction in terms of payability for CO2-free products. The lightweight and compactness, of course, also gives a very good retrofitability. As you can see here as an example on the refinery in Antwerp, there's not much room to fit CO2 capture plants anywhere in the area. So based on this 3C technology, you could actually mount it on top of steel structures and have it placed wherever you would like. In terms of OPEX, the process technology itself is quite equal to conventional technology, but because the high G forces we are using to distribute the solvents, we could utilize a lot more viscous solvents, giving us the opportunity to have more efficient solvents and a lot of higher degree of freedom on which solvent to choose. So we could use the optimal solvent for each point of emission. If you swap slides again. We have been doing pre-feasibility study for maritime CO2 capture. Because of the very small size and a light weight, we find that it's feasible to put this on ships and actually capture CO2 from the propulsion systems on the ships. We have performed a pre-feasibility study with very promising results. And we're working with several shipping providers for potential demos in 2022 and be market ready in 2023. And that timeline is approximately the same as we have on the conventional or the main scope with the onshore and offshore CO2 capture units. Today we are capturing CO2 at our pilot plant, which is a 10 ton per day pilot, and it's located now at the Equinor test facilities in Porsgrunn in Norway. As you can see, the size is very small and it's placed inside a building, even though it's a 10 ton per day capacity. So it proves our compactness, and it's skid mounted, so it could be transported by truck. If you swap slide again, I think that would be conclusive for my presentation, and I would be glad to answer a few questions at the end if the time allows for it.
Okay, I don't think we've got any questions coming in. A question from me would be, what type of customer are you looking for this kind of product? How, is it industrial sector? I mean, you've talked about maritime, but is this aimed at the industrial sector?
It's industrial, waste energy, power plants. I think it's a matter of where we find it competitive. And if we look to 5 million tons or 10 million tons coal-fired power plants, I think the capex issue would be less significant in the overall cost perspective. But everything in between 10 and 700,000 tons per year in emission, I think we find the sweet spot. So, and the competitiveness of our technology would increase as the need for footprint is higher. So if you have a lack of space to put your plant, I think we would have a large favor.
Brilliant. Thank you very much, Torleif. Very interesting technology. And thanks for your time today. Okay, I'm now going to move on to Ian France of PowerStar, who's going to discuss behind the meter battery storage. Over to you, Ian.
Hello, thank you, Scott, and thank you everyone for joining, and to EMEX for setting all of this up. Thank you. Well, that's just me. So yes, Ian France from PowerStar. What I want to talk about is the business case for behind the meter battery storage, and I believe this is an area that a number of companies have struggled with over recent years. And we've delivered about 31 systems and well over 30 megawatt hours of these solutions. So we've found a systematic way to establish strong business cases. What you can see on the screen is a slide that represents a schematic, and I would direct your eyes first of all to the load. So right at the bottom, there's the site load, and that is obviously going to differ according to the different types of organizations, hospitals, manufacturing, etc., and also to the EV charging load over on the right-hand side. And that's a load that today can be quite small, or it could be very important and very strategic, for example, with an organization that's providing courier services with last mile delivery via electric vehicles. And in either case, in either the short or long term, the EV charging load can provide a challenge to grid capacity and to the ability to maximize the use of renewable energy. So then I would direct your eyes to the 3 grey boxes, and they represent the supply. So on the top left, we've got the incoming supply. That's from the national grid. On the bottom left, we have the controllable local generation, for example, gas-fired CHP. And then just above that to the right, we have the renewable generation, solar and wind, and as examples, and they are not controllable, although to an extent they may be predictable, at least in the very short term. So in terms of the solution, I would then direct your eyes to the red boxes. On the bottom right-hand side, we have the battery energy storage system. The battery can contribute to the business case in a number of ways. The first is that it can store renewable energy that's not used instantaneously, therefore avoiding export. The second is it can enable you to run, for example, your CHP for longer. You might be able to keep generating and store excess electricity in the battery to use at a different time of day, as long as you can use the heat. The system can be programmed to buy electricity during cheap periods and avoiding expensive ones. And some of our clients are now moving to agile pricing, where at 4 o'clock today, they will know the price of every kilowatt hour that they buy the following day in every half-hour period. And in some of those half-hour periods, they'll actually be paid to take electricity. So that can be valuable information to enable you to maximize the use of those types of contract. The battery can be utilized to provide UPS, that's uninterruptible power supply, and that protects the site from the impacts of blackouts and brownouts. And finally, the way that everyone has always used behind the meter battery storage is to derive revenues from the national grid contracts, such as balancing market and FFR. Now, another critical area of the infrastructure is on the left-hand side in the red box, which is the energy optimization system. What that can do is predict the renewable generation in the immediate future to about a 97% accuracy in our case. And also it can predict loads such as the EV charging load, the site load based on the time of day, the weather conditions, etc. It can ensure then that it can also ensure that there's sufficient energy always stored to meet any possible UPS requirements in case of blackout. And it can make real-time decisions to charge or discharge the battery based on rational algorithms and the predictive capability that I've mentioned. It can communicate with site control systems, say to implement load shedding, pre-cooling, preheating, to avoid taking power at times when the grid is under pressure and at times when the power can be more expensive. And we would contend that with the increased electrification of commercial scale power, that any robust net zero strategy needs to include an intelligent, in inverted commas, storage system of this nature. And finally, don't forget the green box. We're great fans of voltage optimization and low loss amorphous core transformers, which can typically save about 6 to 7% of electricity going through every transformer, 3 to 4 year payback on a 50-year asset. So they're always part of our solutions where applicable. Thank you. So here we see how that starts to roll into a financial case. On the left-hand side, we have a graph showing the 15-year revenue predictions from such an investment. This is a real case of a 24/7 manufacturing company. The yellow represents a solar array, and the green represents the guaranteed savings from the voltage optimization. In between that, you've got the light and dark blue, and they represent the grid revenues, the FFR and the balancing market and so on. And then at the top, in the cherry red, you have the savings that the client has deemed applicable to the UPS. And on the right-hand side, if you look at the revenue proportions over the 15 years, you can see that 3/4 of the revenues are pretty much bolted down. You've got the solar PV, which is going to carry on as long as the sun shines. The UPSs are deemed saving by the client, and the voltage optimization in the green is guaranteed. So there's only the quarter, which is really quite variable, and of course that could go up as well as down. So how does all this wrap up into a 15-year cumulative cash flow model? Well, the solar PV alone is shown by the black line, about £1 million of investment, crosses the line at 8 or 9 years, nice and positive after 15 years, and that's going to carry on for many years henceforth. The second line is the amber line, so that increases the capital investment to about £1.5 million. That allows day-night shifting, so energy that's generated during the day can be used in the plant at night and derive grid revenues. That's more positive. And more positive again is the green line, where we extend the battery a little bit more to about a total investment of £1.7 million, but it gives a far better return because it provides resilience for the site and it avoids the impacts of grid blackouts. I think I just did that in 20 seconds under my 7 minutes. How's that, Scott?
There you go. Fantastic. There is a question for you on how small can the systems be? Can I ask you to answer that in the Q&A so that people can see the answer? And Torleif, you've got 3 questions on the Q&A yourself, if you could answer those as well. So thank you very much for that, Ian. We're now going to move to Alexander Pavlov of Atlas Copco Compressors to talk about compressed air heat recovery. Over to you, Alexander.
Good afternoon, everybody. Thank you very much. So if you can please bring up my slides. Yeah, so Atlas Copco is a global manufacturer for compressor systems, vacuum, industrial tools, construction tools as well. So if you please go and maybe jump over. Yeah, so that's who we are. What I really want to speak about today is, of course, importance of the energy aspect when we speak about compressed air. So actually, it's normally about 12% of the total industrial consumption for electricity. So and compressors are used absolutely in all the industries. So in any factory you would find compressed air system, and they are big consumers of energy. So the focus has to be always there. What is very special also about compressors, because a lot of heat is created when air is compressed by a compressor, and I believe there is still a huge potential to all of us to recover that heat. So more and more installations have energy recovery systems included, and we have a lot of great reference cases. But just on the right side there, theoretically, if we would just assume that all the compressors which are installed in the UK would be connected to the energy recovery, and we will be recovering all that heat which we otherwise release. So these are just astonishing numbers, that we can potentially recuperate. So going into the technology, so on the next slide, basically, if we don't go to any more details, compressor takes atmospheric air at the inlet and compresses the air at the outlet. So on most of industrial applications would be around 7 to 10 bar pressure, and then it takes obviously electrical energy at the input, and a lot of heat is then released during the compression stage. So and that heat can be recaptured, and in the form of hot water, then this energy can be recovered. And there are a lot of points on if we take oil-free screw air compressor, which typically has 2 compression stages and oil cooler and intercoolers. So there are 5 points where energy can be, the heat can be picked, and our energy recovery compressors, which have this option included, provides that. So basically, for an oil-free compressor, we speak about 90% of the input electrical energy can be recovered in the form of hot water, and it's a high degree heat, so we speak about 90 degrees Celsius. So then the best application is obviously, the steam boilers, the makeup water for the steam boilers, and often it's also located very close to each other. So those are just, perfect applications. But not only the oil-free water-cooled compressors. If we go to the next one, yeah, so that's how it works with the water-cooled compressor, which you have on the left side. We have a big range of the standard energy recovery units, which are actually controlled and because not all the heat would be taken by the consumer, so it would be making sure that the water which returns to a compressor is always controlled at the stable temperature, no matter how much heat is taken by a consumer. So we have also those kind of modular systems, products, which are, really plug and play, and can be integrated in most of existing installations as well. But also if it's an air-cooled in a smaller factories, typically it's oil injected air-cooled compressor which is used, and there obviously a lot of heat can be recovered from oil, because oil is used as a lubricant and as a cooling media as well. So and there we can connect also, as you see on this picture, small energy recovery modules, which are heat exchangers, oil to water, and we can recover also all the heat from oil, and then the hot water can be provided to any applications in this case as well. So also I put there some example in the numbers. We can translate it also of course in the monetary terms, and it's just astonishing how much energy can be recovered. And another thing we are introducing this year is also a very compact and modular screw expanders. So basically our core technology, which is a screw elements for compression, we can also rotate in another direction. So and then we just launched this year a number of expanders, very compact units. So anywhere where pressure, incoming pressure would be higher than the outgoing. For example, it can work with the natural gas system. If you get a gas on pipeline and you need to reduce the pressure for your factory, so that would be a perfect application. Then through this expansion, we can obviously turn a generator and generate electricity out of that. So it can work with steam, it can work with natural gas and nitrogen, so many other examples as well.
Thank you, Alexander.
Yep.
All right, we're gonna move forward a little bit more. So, do we have Bryony Turner with us?
Hello everyone, thank you very much for having me here today at EMEX. I'm going to take you through a whistle-stop tour of some really exciting advances in the space world with regard to the net zero agenda and climate action. As Graham Peters pointed out, the climate crisis needs a new industrial revolution that doesn't necessarily have to be on this planet. So let me try and convince you about that. Next slide, please. So Space for Climate is a group that unites UK expertise in climate satellite data. It's my job to coordinate it. We span government, industry, academia, and the third sector, and everyone in the group is involved somewhere along the data supply chain in either sort of designing and devising and building satellite missions capable of bringing down climate data, or processing those or analysing those and turning them into sort of decision support tools. I'm going to give you a bit of a whirlwind tour of that. I think it's quite important to highlight to the EMEX audience that one of the reasons that the group has formed and is acting to raise the profile of space-enabled climate expertise and services is that there's been a huge amount of public investment, not just by the UK, but many other countries internationally, to produce robust climate data sets. And whilst they've predominantly been used from science perspective for monitoring Earth and to understand how our climate's changing, they also can be used to inform climate action, which I hope I will be able to convince you of. So we connect users to producers. So I just mentioned we go right from, we've got expertise in the group that build and design new satellite missions. I'm going to talk to you in a moment about microcarb. And then I've just sort of shown a few, tried to make it a bit more tangible with some images, showing you some CO2 emissions satellite data there. So the data is then collated. There's a lot of verification and quality assurance. And then you have the kind of information translation. It's very big data. So you can see an example there from NASA of carbon dioxide anomalies. So it gives an idea of sources and sinks. And then value-added services, which I'll come on to an example there by the Institute for Environmental Analytics, which I think you'll find interesting in renewable energy. There's a new mission that now spot the deliberate error. I corrected it in one place on the slide and didn't manage to correct it on the first line. The microcarbon mission, a very exciting mission, is going to be measuring sources and sinks of carbon dioxide, and it will have a city sweep mapping mode, which is going to be really, really interesting. You can actually see the carbon flux. It's not just have a carbon emissions counting, but what's actually generating emissions and what is actually absorbing them and acting as a source, both for anthropogenic emissions, but also the natural environment. It was due to launch in 2020, but the satellite building has been delayed by COVID. So it will now be scheduled to launch in 2022. Next up, I've got an example of, sort of giving you a taster of a satellite mission that's coming. We'll be bringing new kind of carbon dioxide data, but there still is existing data sets out there, including carbon dioxide, but also other greenhouse gas emissions. So an example here from Airbus. So Airbus have over 3 decades of experience in asset level monitoring. And we have in our group the intelligence bit of Airbus that works with the climate satellite data aspect. So combine the asset level monitoring that they're very good at, and they're sort of processing a big petabytes of data with climate data. I didn't have a carbon emissions example to give you here, but I've got the example here from Sentinel-5P, where they very quickly turned around the nitrogen dioxide emissions to look at the impact of the lockdown on the UK. So the point being with this image is to say that, yes, you can look at the sort of asset level monitoring, but also you can task and look at political boundaries as well. Next slide, please. An example of where we're kind of pushing ahead with new types of analytics is to look at questions we had from land managers, and it was really led by a peatland scientist who actually wanted to know, can we not only reduce emissions from peatlands, but also help contribute to other climate action as well? So could we reduce surface albedo, so the temperature, and help reduce heat risk with interventions that are restoring peatlands? So this requires a lot of data and a lot of near real-time data. A similar came forward with their data cube to harness the Earth observation data. And if anyone is interested in this, we built the data cube is built by Similar for the UK. So you are welcome. We've got the ability to have a number of people test it out, and it could have other uses as well as for peatland monitoring. So this one I thought you'd be particularly interested to an EMEX audience, and in fact the IEA did come on stand for those of you who might have visited the Space for Climate stand at EMEX last year. So the Institute for Environmental Analytics have developed a renewable energy space analytics tool, and they combine ground-based observations, weather data and satellite data to help basically do everything, as far as I could see, with renewable energy scenario testing, planning. We heard earlier about the sort of working out the power. I think it could be interesting with the battery side of things. Look at the financial viability. They can run different scenarios. So one of the important things why you need the weather data, I mean, some of you will be more expert in this than I, but to understand the downtime under different scenarios, and particularly where you've got mixes of renewable energy. So this tool was actually developed initially to help small island developing state nations via UK Space Agency funding to meet their renewable energy targets and be more energy independent. And I think another thing to point out about the efficiencies that can be devised with these analytics is also that you can more accurately calculate what's your reserve fossil fuel that you need to have and potentially not need to be holding as much in storage. So I just wanted to end, this is my penultimate slide actually, but you might have seen a news release about this. The UK government has launched a research project, a scoping project being led by Fraser Nash Consultancy with Oxford Economics to explore space-based solar power systems. The advantages in space, of course, is that the sun never sets. However, I wanted to pick up on what Laura Riesdale was saying earlier, that, you know, data, and particularly these kind of petabytes of data that are involved in the analytics I've been talking about, you know, they have an energy cost too. This is something the space sector is very conscious of. Some of those platforms I showed you with the analytics, the whole point of them, like a data cube or a cloud platform, is that you can actually have greater efficiency of data, because everyone is not downloading the data onto their own computer and then analyzing it. It's cloud enabled. I just wanted to end now with this point that whilst we're talking about net zero and these efforts for the zero carbon agenda, if you actually look at the UNFCCC Race to Zero, it is very specific about it being a healthy, resilient, low carbon recovery. And so I just wanted to end with saying that the Space for Climate Group has been working particularly with the financial services sector, who will all be investing in your types of products, to help with climate risk disclosure tools and services, so that any product that's being developed for net zero needs to be able to stand the test of its asset lifetime with the changes in climate we're already anticipating. Thank you very much.
Thank you very much, Bryony. That's really interesting stuff. And as a space geek myself, I'm very interested to hear more about that. If you can keep your eye on the Q&A, if everybody's got any questions for you, if you could answer those so that we can all see the answers, that would be absolutely fantastic. We're gonna carry on with the same schedule and move to Matthew Truella, Managing Director of Kenza Contracting now, and then we'll come back to Lydia and Jeff shortly. Okay, over to you, Matthew.
Hi there, it's actually David Broom. I was dropped in at the last minute as Matthew's unavailable today, so I've been asked to kind of step in his place. This is slightly challenging as well. I've already had a call this morning about this. It took me an hour and a half to properly explain what we do, so to do it in 5 minutes is a bit of a challenge, so I'll crack straight on if we can get the slides up. Yeah, absolutely. I'm David Broom from Kenza Contracting. We're a national ground source heat pump contractor, and our sister business, Kenza Heat Pumps, is a ground source heat pump manufacturing business. We've been building ground source heat pumps in the UK for 20 years. Have you got my slides available? There you go. If we could just skip straight on to the next one. So just very briefly, just to touch on ground source heat pumps and how they work. Essentially what we do is we take a large volume of low grade heat, we harness that heat and we compress it and upgrade it into useful heat for homes and businesses. And the key element of it is the closer the temperatures are between where we take the energy from and where we're putting it into, closer those two temperatures are, the less work the compressor has to do and the more efficient the system will operate. And heat pumps seem to be coming towards the forefront of people's minds. We have to spend a lot less time explaining the technology now, which is great. What we have is a slightly different application for the technology than your standard kind of domestic individual installations. So next slide, please. So what Kenza have been pioneering over the last 7 or 8 years is what's become known as kind of 5th generation district heating, or ambient loop district heating. And the heating sector was referred to as the elephant in the room earlier. So hopefully we can start answering some of those questions as to how we deliver on these challenges. So what we do is we take traditional heating and we kind of flip it on its head a little bit, and we use the low temperature circuit that connects all of the heat pumps together to distribute energy around the circuit, and then we upgrade the heat to useful heat at the point of use. So typically this is within individual buildings, and we've done lots of social housing retrofit, including tower blocks, where we've taken out mains gas combi boilers, replaced it with ground source heat pumps with individual units within each dwelling, providing space heating and domestic hot water, improving compliancy, but also providing a solution that doesn't impact on kind of fuel poverty, because we're not increasing the running cost to the residents compared to mains gas. The benefit of doing it that way with rather than doing a central plant is that all of the network is on the cold side rather than the hot side of the heat pump. So we design out any system distribution losses around the circuit. It also means that all of the billing is individual to each end user. So the heat pump is downstream of the end user's electric meter. So they just pay for their heat as part of their electric bill, and they can do away with their gas standing charge. So that makes another saving. And that network, as I say, operates typically anywhere from 2 to 8 degrees, but can operate up to 20 degrees, connecting all of those heat pumps together if we've got some waste heat on the circuit. So the heat can be developed through closed loop boreholes, so drilling down to a couple of 100 meters to take the energy out of the ground. We can use groundwater, so energy available in aquifers, and we can also use surface water as well. So there's lots of residual energy available in the ground around us. But what we can also do is we can harness lots of forms of waste heat. Because we've got that circuit running at ambient temperature, it can equally be used for space cooling and process cooling as well as heating. So I was very interested to see Brian's mention of kind of water-cooled data centers earlier. We could harness all of that energy, put that into our ambient loop network and distribute that amongst all of the heat pumps on the circuit to deliver, as I say, space heating and hot water. And what that also allows us to do is have heat pumps sized and specified to each individual load at any point on the circuit. So again, if you've got more industrial or commercial applications, larger and high temperature heat pumps can be used to service that. And then low temperature heat pumps and heat pumps providing kind of small scale heating and domestic hot water for dwellings can also be used. So that ambient loop circuit then becomes kind of a heating and cooling loop that can be used anywhere amongst the circuit to generate heating and cooling. And as I say, process cooling can also be used. Energy from waste, kind of connections to any other form of waste heat can come in. And again, that also assists with the business model in terms of reducing costs for cooling as well as heating. What we can then also do is optimize the operation of the heat pump based on the variable cost of electricity. So even without having any thermal or battery storage, we can actually use the building physics to move around how we operate the heat pumps, still maintaining the performance and comfort levels that you're looking at, but avoiding the peaks of electricity, therefore reducing the operating cost and also the carbon emissions. So if we go on to the next slide, please. So just by moving kind of 4 half-hourly slots of the heat pump operation into lower peak, lower cost operating times, we can save kind of 15 to 20% of operating costs. And all that basically means is we bring the heat pumps on slightly earlier, we heat to a slightly higher temperature and then turn them off again and let the building cool itself down when electricity becomes more expensive. And we see this as being a big part of the future of the rollout of renewable heat in the UK, and that's how we look to combine with other renewable generation and electrical storage. Next slide, please. So just as a practical example, we are kind of nearing completion on the first phase of the Oxford Super Hub project, which is the installation of 60 dwellings retrofitted into social housing properties for stonewater housing. These all feature individual heat pumps connected to a shared ground loop and all installed with smart controls that allow us to provide that level of home automation and optimization, reducing the running costs of the residents even further by switching the operation of the heat pump into off-peak times. And then as we kind of, that scheme, part of that scheme is also kind of large scale transmission connected battery storage and bringing the whole thing together to basically ensure that as far as possible, localized energy is used to provide the operation for those heat pumps. So I don't know how I'm doing for time. I fairly well rattled through that and skipped on lots of detail. So if anybody wants to know any more, please ask the questions or get in touch separately. I'd be more than happy to talk through a little more length and a little more detail. But yeah, we're certainly confident that ground source heat pumps and ambient temperature district heating has got a big part to play in the decarbonisation of heat in the UK.
Thank you, David. Absolutely agree with you. I think heat pumps are going to play a massive part in heat decarbonisation. So thank you very much for giving your pitch. Any questions for David, please pop them on the Q&A. And David, if you could answer those so that we can all see. Hi, Lydia.
Hello, Scott.
Hi.
How are you? Great pleasure to be here.
Excellent. Over to you. You have 7 minutes. Go for it.
Thank you. So I would like to start my presentation to show you a building that displays a 62-foot wide 15-digit electronic clock And you can pass to the next slide, please. Yes. And this clock is very important because it displays a deadline for us to take decisive actions to keep global warming under 1.5 degrees, comparing to the pre-industrial levels. So this clock shows we only have 7 years left to deplete the 420 gigatons of CO2 budget to burn. So no need to say how much this brings the future into focus, and time really urges for us to find a realistic solution to turn this out. We in our company really believe that biochar is the solution for these problems. So thank you. So biochar, it's basically charcoal, but differently from the charcoal that we are used to use for grill purposes, which is basically or technically made from wood. This biochar is basically made from any type of biomass. So when you heat this biomass in an oxygen starvation environment, you thermally decompose this biomass into 3 things. You can pass on, please. You have combustible gases, you have tar and oils, and you have the solid compose, which we call biochar. And this process is known by pyrolysis. So when you take a look in a microscope at this compound, you can see it's full of channels and it has a lot of open area, which gives it 2 fundamental properties: highly porous and with a huge surface. And more, this surface area is weakly negative, which is great to drawing minerals into its surface. So this is the material used for centuries and millennia to amend soils. And you can pass, please. You can see how different the yield of crops can be when you really use biochar and you don't. So making biochar is not a new technology. It's the most old industry art that we can think of, and pyrolyzing organic debris to make gases is not new either. Now, what is new is that we can use this substance apart from soil amendment to combat climate change. And how does that happen? A little biology will explain. Next slide, please. So plants pull out what is arguably life's most impressive magic trick. From plain daylight and a bit of water and minerals from the soil, they transform carbon dioxide into pure oxygen to build their mass. So when we use this mass and you pyrolyze it, we are trapping the carbon of this constitution. Trapping it in a very, very stable structure that takes thousands of years to decay and contains around 70% of carbon in it. So apart from having great benefits to the soil, we can trap carbon dioxide from the atmosphere. And producing biochar massively in a large scale, we are able to offset 12% of human greenhouse gas production. Next slide, please. This chart represents the total CO2 emissions, and it shows that we are far from still slow down our carbon emissions. So curtailing GHG emissions alone will not be enough to decarbonization. And here is where biochar is different. Because in addition to avoiding emissions, biochar sequesters carbon in the soil, removing it from the atmosphere and working as a long-lasting and stable sink. So you can pass the next slide, please. We call this carbon negative, and being carbon negative is planet positive. This technology positively impacts 11 out of 17 sustainable development goals set up by United Nations, revealing that biochar is a really, really powerful tool for a variety of environmental challenges that we face today. We all know that our economy is totally dependent on petrochemics, and we are all paying the price with eroded soils, polluted waterways, oceanic dead zones, and other externalities that pile onto the global threat of sustainable development goals. But soil holds the key. Next, please. Earth soils contains more carbon than the atmosphere and the terrestrial ecosystems combined. And yet we are losing them at a rate approaching 100 tons a year. One inch of soil takes 100 of years to be built, but biochar can jumpstart soil formation. So in conclusion, by globally adopting these solid building strategies, along with technologies to wean us off fossil fuels, it is our belief that we can not only delay our climate clock, but also put carbon back where it belongs, in the soil. Thank you.
Thank you very much. That's
Thank
very great. Thank you. Okay, so we don't have any time for any questions for Lydia. So where are we moving now? Jeff Edwards from Axair Fans Limited. Jeff, over to you.
There you go. Can you hear me now?
Yes, we can. Thank you.
Good. Sorry about that. Okay, good morning, Scott. Thank you very much for the introduction. My name's Jeff Edwards. I work for Axair Fans as the Business Development Director. I'm going to talk to you today about the AHU refurbishment, specifically using EC fan grids. First slide, please. Thank you. The core of the EC fan grid is the EC motor. The EC motor is a combination of a DC motor and an AC motor. And what you get with that is the energy efficiency and controllability of the DC motor with the relative ease and flexibility of the readily available and well-distributed AC power. The primary two advantages of the EC motor are the energy efficiencies you get and the controllability you can have over the motor. That provides really meaningful running cost reductions, both from an energy consumption point of view and a maintenance point of view. And with the onboard connectivity, the interrogation of the motor to give you greater insights into the performance of your HVAC capital equipment is quite useful as well. So the EC fan grid itself is the addition of the EC motor to an impeller that will move the air, and then using multiples of these. So it is in effect a fan grid, a fan array. There are lots of good key benefits to that, but for the sake of being quick, I've listed just the top three really. Now the flexibility of the solution is really one of the nice things about it. You can have almost any combination of internal configuration of an AHU combined with really any size of performance, so airflow and pressure loss systems. Because of the array or modular nature of the fan grid, there is an inherent inbuilt redundancy, which allows for single or even multiple fan failures, but the solution as a whole is still providing a minimum airflow, or at least, or even 100% of the requirement at the initial design stage. The efficiency, with the enhanced control, with using EC motors, the system can save up to 30%. Occasionally it can be more, and that is very meaningful. If I could have the next slide, please. At 30% savings, you can comfortably get ROIs of down to about 1.5 years, 2 years, 3 years is typical. Here we have a small application case study. This was actually in Germany at a banknote printing site. The image on the left is the original fan that was installed, and it was replaced with the fan grid that you can see on the right. The original 2 fans were consuming over 67 kilowatts per hour, and the replacement fan grids reduced that consumption down to 46 kilowatt hours. You can see there that the CO2 reductions were dropped by 100 tons a year, and the payback period was only 18 months. If I could have the last slide, please. Okay, so what does a project delivery look like from AXA? There would be an initial site assessment. Probably that would be a desktop study by myself from my office in conjunction with a customer side, trying to understand what they want to achieve from their project and their performance parameters. That would likely lead to an on-site survey, and that can be depending on, again, what is wanted to be achieved. That could just be simply assessing the site, the premises itself, the internal measurements of the AHU, site access, so on and so forth. If a more in-depth understanding of the savings, carbon emission reductions, electrical consumption savings is wanted, then we can do a full validation survey, so the whole parameter of the AHU are defined. Following those site surveys, a quote is provided, and there's a back and forth about the different options. There are almost always 2 or 3 different ways of going about delivering the project. If the project was to go ahead, any site surveys that have been charged are deducted from the value of the quote, and then we go forward into delivering the project. So thank you very much, everybody. That's me done, just about under time.
Thanks, Jeff. Very much appreciated. Okay, so now we're going to move to Andy Bray, Head of Sales at IEM, to talk about predictive maintenance in renewable energy assets.
Hi, Scott. Good morning. Hopefully you can all hear me.
Yes, and see you.
Excellent stuff. Good stuff. Good stuff. Well, thank you very much for the invitation. I think my talk, interestingly, having listened to a number of the others, will work across 1 or 2 of the others. I think there's some link with Brian's, Ian's, and Bryony's. So very briefly on who we are. I work for IEM. We've been going for around 15 years. If you could go to the next slide, we provide software for renewable services and renewable products on a worldwide basis. We get data from, interestingly, listening to Bryony, from satellites, from drones, from data loggers, from technical specs, and one of the key skills is blending all the data in. So we provide services across the world in the places you can see, and we provide it in PV, wind, storage, microgrids, and and starting to look into e-mobility. So the talk today will be around predictive maintenance. So on a recent webinar I attended, somebody mentioned a figure of about $500 billion will be needed just for some major countries, just for the investment in wind and PV to hit the world targets. I think if you add in the figures for battery storage, EV, and all the other investments into renewable, that figure will be undoubtedly be higher than that. So what are people going to need to want to do with their assets? Undoubtedly, the investment in all these assets will need to be optimized. So where does predictive maintenance fit into that? Some maintenance schedules can sit at this end, which is reactive. It's great, if something goes wrong, you go and fix it. But as a basic practicality, the more advanced your intelligence, the more advanced the data, the better you actually start to use that data, then it really does drive some greater value. This is an excellent report from Deloitte. I think I've referenced it on the next slide, as to where then the value you can get by using predictive maintenance. Sorry, if you could just pop back to the next slide. So So predictive maintenance comes from a number of sources. It comes from technical specs, it comes from previous performance, it comes from analysis of how the plant and the equipment is actually using. And as people, both end users as organizations, are looking to really use and invest more into renewable energy, we believe that predictive maintenance really has to be part of your program going forward. Next slide, please. So the Deloitte paper, again, I won't read all of those ones out, but you can see the values that predictive maintenance can really drive the improvements in uptime, in the improvements in performance and output. And we did a recent webinar where, from talking to our customers, by adding in predictive maintenance, it increases the return on investment on their PV plants by a minimum of 5%. So if you're investing in PV, if you're looking at other areas, then that really just shows the value that predictive maintenance can bring. So if you go to the next slide, please. So what's our experience in predictive maintenance? We work around PVs, I've mentioned. We do predictive maintenance for hydro. We do predictive maintenance. I'll put my false teeth in for wind turbines. And again, by combining and blending a number of datas for PV, it could be identifying hotspots, inverter issues, etc. We provide a web-based platform for our customers to really have high quality, intelligent data. And we've done a lot of work on the predictive side, and we found that over 90% of our estimates where there's going to be an issue from predictive maintenance prove to be accurate, which I think if you're providing any type of forecast, that's very, very impressive numbers. Next slide, please. So one of the things that we would like to do, and this is to everybody, and instantly that I think the conversations from Brian and Ian around the whole battery space, we're looking to now add predictive maintenance for battery storage. Battery storage will be huge for microgrids, smart grids. I think the battery EV combination will undoubtedly be growing hugely over the next few period, EV charging plants, etc. So we're looking to try and see, can we add predictive maintenance using our skills and expertise, and to develop that as a service, as an offering. Next slide, please. So how might this look like? This is a very sort of simple concept. So you have the battery storage maintenance here by adding in a number of sources of data. So it could be sort of the technical specs, wind forecast, and a number of other areas, using the machine models and using the artificial intelligence tools that we have to try and provide a simple output for organizations to identify where there are going to be issues with predictive maintenance. Next slide, please. So again, this is a bit more detail to try and identify, to look at some issues for customers in terms of monitoring, technical support, and then to help people with power management, black star mode, and peak load shaving. So this is an idea we'd be very keen to talk to people about, and I think it's very quick. I've rushed through mine, so I'm probably slightly ahead of time. Scott, you'll be pleased.
Well done. Thank you very much, Andrew. And it's great to hear somebody else talking about the importance of maintenance and how maintenance impacts on performance. Absolutely fantastic. Thank you very much. Okay, so we're now going to move to Chris Davis, who's UK Sales Manager of Hissopt. Did I get that right? Talking about digitizing HVAC design for low carbon performance. Over to you, Chris.
Thank you, Scott, for that. I'm Chris Davis. I'm the UK manager for a company called Hissopt. We produce design and simulation software for optimizing commercial scale heating and cooling systems. And what I'm going to talk to you about today is how digitization and digital twin technology can be used to help both building owners and engineering companies to optimize and improve HVAC performance to both lower carbon emissions as we head towards a low net zero carbon future, and also to tackle energy cost reduction. Oops, I need to move my notes on here. So yeah, in the interest of time, I think everyone understands what the issue is in terms of decarbonisation and the role of heat and cooling in buildings within that. So I won't dwell on that for too much. But also, as we drive towards an economic recovery, the energy cost savings from optimising heating and cooling are also significant and important as well. So all this might mean, a number of things. Certainly moving away from fossil fuels for heating, and introducing, technologies such as heat pumps, connecting more buildings to heat networks, making more use of waste heat, for example, or indeed just optimizing existing installations, because there's so much inefficiency in actually most heating and cooling installations. And of course, the really big challenge is how to do this in both existing buildings as well as new ones. And one of the major challenges here is around the way in the traditional approach to the way heating and cooling systems are designed, which typically ends up in efficiency on paper and in theory, but rarely actually in practice. And the major reason for this is lack of transparency. So, for example, most systems, whether they be heating systems or cooling systems, they're designed for a single peak load condition, but without any knowledge of how that system is really going to behave under part load conditions, where they spend 99% of the year actually operating. We're also seeing designs now for low energy, low carbon systems becoming much more complex. We're seeing lots of high cost green technologies being introduced, heat pumps and CHPs, thermal storage, heat recovery systems, but there's not enough knowledge and thought given to how the whole system will integrate together and perform in actual use. So the performance of these technologies are not transparent to anybody at the design stage. No one's taking that holistic approach. And then we also have an issue where we start to see this performance gap between design intent and how systems actually perform in real life as well. So all of this means we kind of need this this system-based approach. So my slide here was supposed to build up, and it's supposed to be a cool little video, but never mind. I'll just talk through it. So this is where digitization technologies really start to help, actually. Firstly, by introducing measurable performance at the design stage, and then secondly, by ensuring that the integrity of an optimized design is translated into the as-built installation. And this is done in two ways. So firstly, as a design and a simulation tool, a digital twin or digital model of the installation can simulate and predict how it will perform under both full and part load conditions in real life. So the design can be optimized to remove any hydraulic inefficiencies and make sure everything is calculated properly. And what this allows is then multiple iterations of a system design to be compared side by side and compared objectively in terms of energy use, energy costs, carbon emissions, comfort, and so on. So the right commercial and engineering choices are made at the early stages. Secondly, then, it's about securing the integrity of the design into the installation and commissioning phases. And the whole idea then is that the digital model is transferable at every stage of the process, from design all the way through to installation, commissioning, and handover. So you have this seamless knowledge of how that installation is supposed to perform, and even down to the point of how it should be commissioned correctly at that point of a project. Now, what I was going to show you here, the kind of video is not working, but essentially what a digital twin looks like is a two-dimensional CAD drawing, but sat behind it is a mathematical model that understands exactly how all of that system operates and kind of works together. And maybe you'll see a still of that in just a second. And then finally, the digital model that's created becomes an asset for the operator. So when the system's handed over, they not only know what that system is, but also how it's supposed to perform. If you can flick on to the next slide, please. So here's an example of this. You can see on the right-hand side there, that's a little digital twin I was talking about. It's that mathematical model that understands how it all works. This example actually is from a recent renovation project we've just completed with a large private sector company. They were looking to replace some existing gas boilers with and add some air source heat pumps into that installation as well to provide part of the heating. Now, what you can see here in the brown boxes there is what you get from the design from the engineering sector today. This is a typical M&E design. Everything's based on a peak load condition. When we digitize that design to actually check it, what we can show straight away, we show this to the client, is that actually the contribution from the heat pumps they were going to have was actually only about 10% of the annual energy contribution. cost savings will be between about 14% of the energy cost per year, and maybe around 17% carbon savings over their older existing gas boiler system. By going through it was obvious right away that the design choices that were being made there would limit the optimal performance of the new boilers and the heat pumps. Now, going through an optimization exercise using digital tools to simulate different improvement options, you can see the impact. So with the same equipment, the design was just changed hydraulically. You can see we've more than doubled the annual energy cost saving and almost tripled the carbon saving. Same building, same equipment, just integrated hydraulically differently. That's what we mean by bringing transparency into the design stage. Last slide, please, if you can, Chris. There we go. So yeah, in conclusion, the digitization of HVAC systems brings transparency of how systems will perform at the design stage and helps to ensure that design intent is translated into the actual installation to maximize energy cost savings and carbon savings as we look to move towards non-traditional technologies. So thanks for listening. My contact details are on the screen. If you're a building owner and looking at decarbonising heat or cooling in any of your buildings, please feel free to get in touch if you'd like to know more. Thanks very much.
Thank you very much, Chris. That was a great way to finish them all up. And thank you to all of our speakers today. We're glad you had the opportunity to present your technologies without being able to see people in person at EMEX. I'm now going to pass across to Jason to just do a few closing words before we close the session.
Thank you, Scott, and thank you for managing that session. It's this is so far from ideal. We've spent 7 years building EMEX and the community, and it works so much better when everyone is together. It works so much better when you can bump into people that maybe you haven't seen in a long time or not met before at all, but can share a conversation that triggers something. Zoom's been terrific this year for sharing messages that are planned, but it doesn't let the magic happen. It doesn't let the impromptu conversations. So we hope you'll all join us next year. We're very excited to build up to a real celebration of life, hopefully getting back to a new sort of normality. But it's also great to have the opportunity over the last week or so to work with so many people that have been involved with the EMA and EMEX over the years and put together a great program. So thank you, Scott. Thank you, Rupert, I think, who's run off to vote in Parliament, and everyone else who's given their time. Also very pleased that we had some technology people able to give a presentation. We're going to share lots of information post-event, including a cool link to a 3D walk around of last year's show, so we can get you in the mood for better times to come. But thank you. That's it. We'll call it a wrap.
Thank you very much, Jason. Thank you very much, everybody. Bye.